Okay, we're going to finish talking about some related rates examples that we started today in class. Okay, and just to review just a few minutes on these concepts. When it talks about at what rate is a quality changing or something or some kind of something you can measure how it's changing, that's called a rate of change. And you know a rate of change is a derivative. But these particular quantities are changing with respect to over time. So we're going to take the derivative with respect to time, which means we're going to use implicit differentiation. So turn to the third page, example 4. And here are some different type problems we didn't finish today. Be a good day to take a homework note quiz tomorrow in class. See if you understand these concepts. All right, an airplane is flying on a flight path that will take it directly over a radar tracking station. There's the tracking station. The plane is flying this way. If S is decreasing at a rate of 400 miles per hour, when S is equal to 10 miles, what is the speed of the plane? So you've got a lot of words going on here. Let's first of all notice that it said S is decreasing at a rate. So then that's a rate of change. And speed is the absolute value of velocity. So we're going to have to remember how these things fit together. Okay, so those are pieces of information we're going to use as we go along. They're not going to be used at the beginning, but they can be. First, we know we're going to identify our rate of change. Our rate of change is to S. It's decreasing, so it's negative. So ds dt equals negative 400 miles per hour. All right. Next, we have to get a relationship between Sx and whatever's happening with the plane. So notice that this relationship makes a nice right triangle, and we know that x squared plus 6 squared equals s squared. So now we have a relationship. We can differentiate with respect to time. So that's 2x dx dt, and you know the derivative constant is 0. And 2s ds dt. So we're getting a little bit closer. We want to find what's the speed of the plane. So the ground speed is the rate of change of x. So I'm going to solve this for dx dt. So that's 2s over 2x ds dt. So dx dt equals s over x ds dt. Well, I have a value for ds dt, negative 400 miles per hour. I have a value for s, 10, but I need a value for x. This is a case when you go back to the original relationship, sketch the diagram, and since we're going to look at what's happening specifically at one time period, I'm going to say when s is 10, does x have a value? Well, yeah, this is a Pythagorean triple triangle. It's a right triangle. So if this is 6 and this is 10, that missing side has to be 8. So when s is 10, x is going to be 8 specifically. So then I can plug in that information. dx dt is equal to 10 miles over 8 miles. And dx dt is negative 400 miles per hour. The miles are going to drop out. Simplify a little bit more. So dx dt equals negative 500 miles per hour. But because we said it was speed, that's the magnitude of velocity, we're going to take the absolute value of it. Its speed is 500 miles per hour. But it makes sense that this would be negative. Think about why, and we're probably going to see that on the homework note quiz tomorrow. All right, your next example. A conical tank has a height of 3 meters, radius 2 meters at the top. Water flows in at a rate of 2 meters cubed per minute. All right, there's a rate of change. And because it's cubic, you know this is rate of change of volume. So dv dt equals 2 meters cubed per minute. How fast is the water level rising when it's at 2 meters? Means what is the rate of change of the water, the height of the water, when its height is at 2 meters. So sometimes you have to be able to interpret what the question means using the grammar they give you. All right, so I got volume, I got height, I got a cone. Let's sketch a quick diagram. And we know at the base of the cone, the radius is 2, and the height of the cone is 3. And so that means I've got volume, so I'm going to write down my volume equation. Volume is 1/3 area of the base times the height. And we're going to be taking the rate of change with respect to time. So I'm going to go ahead and start to do that. But I notice that when I do that, I'm going to have two variables. That means I'm going to do the product rule. Well, that's more algebra. I would prefer not to do that product rule. So let's see if we can get a relationship between R and H before we start the problem. Remember, the water is flowing in. As the water flows in, the shape that the water makes is filling it up. It takes on the dimensions, takes on the same shape as the container. Well, that pink thing is also a cone itself, meaning the water is also making a conical shape. If I'm going to stop at any time for any time t, then that would be the radius, and that would be, I don't know what it is specifically because I'm going to look at it at time when the height is 2, but I want this to work for any h, for any time. So I do know I can make that relationship. I can make this type cone figure, and if I put this figure on the outside and this on inside of it, fit it right in there. Notice that the radius and the height are perpendicular to each other, so I've got a nice triangle relationship. And because these two angles are right angles and they both share an angle, then these two triangles are similar triangles. And if you have similar triangles, that means corresponding sides of similar polygons are in proportion. We like that because now I can make an equation. So I'm going to go from big to small, and remember it has to be corresponding sides. So 2 to R is equal to 3 to H. All right, so now I've got a relationship between R and H. Let me go back to my original equation because I didn't want two variables. I got to make a decision which one I don't want. Well, since I want to see how the height is changing at 2 meters, I don't want an R in my problem. If I don't want an R, I want R in terms of H, if I can do that. Let's see if I can make R in terms of H with this expression. So 2H equals 3R. R is equal to 2H over 3. Yay, that makes my life a little bit easier. So let's take that expression. R now is in terms of H, and let's substitute 1/3 pi 2H over 3 squared times H. And doing a little bit more algebra, 4H squared over 9. So before I take the volume, I'm going to get everything simplified. So that's 4 over 27 pi H cubed. Now we're going to take the derivative with respect to time. And dv dt equals 3 times 4 over 27 pi h squared dh dt. 3 goes into 27 9 times, makes your life a little bit easier. And let's just simplify that a little bit. H squared dh dt. Well, you know a value for dv dt. That's 2. And you know a value for h. You want to find the rate of change of the height of the water when h is 2. Again, doing a little bit more algebra, or in this case, just simplify. And I'm going to solve for dh dt. So that means the 9 is going to go to the numerator, and the denominator is going to be 16 pi meters squared. And let me just write on the back of another piece of paper, give it a little bit more space. There we go. And I know that 2 goes into 16 8 times, so this is going to be 9. And meter squared cancels with meter cubed into meters. Meters per minute over 8 pi. And that makes perfect sense because height should be changing at meters and not meters squared or meters cubed. All right. So those are type problems, just the beginning of the type